All right, I think, I'm late. Time to start. Week 6. So what we're going to do today is to look at active filters. Yes. That's pretty much it. Is there any questions along the project that you need to have answered? Because you really should be starting looking at that in earnest. Okay. Well, the technique that we're going to look at today may be of use. So, anyway, that's some of them. Okay. Well, let's get into it. We've got stuff to get through. So, let's just quickly go through what we did last time. So we looked at advanced op-amps. So current mirror op-amps, like this, of cascade op-amps, is kind of many of the op-amps that we looked at is in that category. They tend to be operational transconductance amplifiers, only gain in the output node, and then you make the output node impedance really high to have a lot of gain, but it is essentially a current output device. It can't drive a resistive load, but it is very fast because it only has one pole, so it's good for that. We also looked at using Fowler cascode rather than telescopic cascode as the as a device. Now that has the advantage that you can put a lot of the bias current in the differential pair, and that would make it a low noise device. You can also easily extend the input range to be rail to rail by adding two differential pairs. I probably should say for the differential pairs here that if you want to do it really well, what you've got to make sure is that the transconductance that you get, which is really the transconductance for the P and the transconductance for the N is summed up, that the total transconduction for the amplifier is constant over the complete common mode range. So the way that you've got to do that, it's easy if you keep the input pair in weak inversion, because then the transconductance is proportional to the current. And then you have either feed forward or feed back system that makes sure that the sum of the two currents, and these are the constant over the entire range. So when you mid-rail where they're both turned on, you just wind down the current in both of these two, for instance. So, but yeah. There's many things that we can't talk about. Okay, we could also boost the output impedance even higher by putting in, super cascodes. What else can we do? We can put an output stage on. So typically what you want to do if you're looking at things like rail to rail is that you want to have a common source type output stage. You don't really want gain in it because you've got plenty of gain in the main amplifier normally, but you want to be able to drive a resistive load, say, so you do something like that with a bias setup. So this is a good output stage for that. But now you do need to have Miller compensation in that, which is a disadvantage. We looked at fully differential, which is essentially just take there's the current mirror op amp, have all the cascodes in that you should have and get rid of this Y here, you have two outputs. Now when you do that, you need to introduce a common mode feedback system. So what you do is you measure the average of the two outputs, and if the average is not the target value mid-rail, then you adjust the common mode feedback voltage there, so you bring it back into the rail, because the common mode feedback is not normally part of your feedback structure that you have. Yeah. Okay. So we looked at a couple of different code feedback. We also looked at a current reference, typical current reference like that. So I'll give you a sort of self-bias so that the transconductance of N1 there becomes 1 divided by R if you size the structure correctly. And then you can derive your currents from that. Now you will get, if you have a resistor there, you will get process variation in that. So sometimes you might want to trim that. And trimming is really quite easy. The concept is really that you, with digital control, this is a normal kind of trimming in a way. With digital control, you switch in and out extra components. It could be capacitors or resistors or transistors, whatever it is you want, but the principle is the same. So you need to store that information somewhere. And that is what we did last time. Any questions?
For the trimming, how would it typical is like if it switch on and off fast enough, the circuit like the output of it, you see that
well, for the trimming, typically what you are after is not some, it's kind of a set and forget type of value. So you don't normally change these values. So only when you boot your circuit up, then you, depending on how they're stored, you switch them on and off. You can store it, it could be pins on the chip, if you have enough pins, or else it could be in some non-volatile memory, or you can stream in calibration data. But it's normally something you do just once. It does, of course, add some parasitics to this, so you get some capacitance in these nodes. You need to make sure that the on-resistance of the switch there is much smaller than that resistance there, so it becomes big. You can also do a series component, or you can put these in parallel instead, and then switch them in and out. So then you've got to have it's kind of the same thing, really. But yeah, so the parasitics is a little bit different in that case. Yeah, I don't know, but normally it's a static thing. Does that answer your question?
yes. So basically, we normally don't care about the transistor, like we can just ignore it.
Well, you want to design it. So if you look at this circuit here, then this is really just, this is a biasing circuit. Yeah. So this uses static current, but there's no signals in here. So it's like 0 D, 0 hertz. Yeah. It's a DC value. So it doesn't really matter if you have capacitance sitting along that. So the capacitance parasitic is not important. Not in this circuit anyway. If you look at this one here, then the other parasitics for the transistor is the on resistance. And you need to make sure the on resistance of the switch there is much smaller than whatever else resistance you have, so you can ignore it. So you've got to size the transistor accordingly. Yeah. But that's not normally difficult to do. There's normally enough, and plenty of headroom there.
So basically, there's no downside.
The downside is that you need to find this information.
Okay.
So that becomes a calibration step. So if you have a production system and you've got a chip, now you've got to find out what the setting is to the chip, and that's expensive. You don't want to do that. Your manager is not going to be happy if you said, "Oh, well, I need a calibration step for that." So it's better if you get around it, but sometimes you can't.
Okay.
Yeah. And the other thing is that once you have determined that, then you've got to store that information somewhere. Now, in most systems, it's not a big drama because you normally have some non-volatile memory somewhere. But if you're making just an op-amp, you don't have that. So it's better if you can design your circuit in such a way that you do not need to calibrate. But very often, that's just too hard, and then you've got to put in a calibration step. Yeah. So there's a downside. Not really from the circuit performance point of view, but how do you manage the calibration? You've got an extra procedural step to use there. Yeah. Okay. Yep.
Are we going to cover bandgap references?
No, it should have been last week, and we ran out of time. Yeah. Sorry. Yeah. if we have some extra time, then then we can do it.
We'll do a fast presentation.
Yeah. Okay. All right. Let's get on with today's topic. So we're going to talk about active filters. So we're going to talk about two classes of filters. The first is GMC filters. And this is an active filter. So active and continuous time filter. Okay, and this is sort of filter you have when you have some kind of sensor here that some signal comes into that. What you normally need to do is to probably have some kind of amplifier, and then what you want to have over here is an ADC. Yeah, so this is a very typical electronic system, but of course, the ADC is typically a discrete time system, so you've got a sample somewhere. So there's going to be a sample and hold sitting somewhere in here. Now you sample it, and you need to make sure that you have, you don't alias, so you have to have a low pass filter here, so anti alias filter sitting there, and that has to be continuous time because otherwise you're just moving the problem. Yeah.
Just a quick note: is the anti-aliasing built into all ADCs or like microcontrollers?
It should be.
Yeah, because I've always wondered. We never low pass filter before sampling. Okay, so it's because it's built into the ADC.
Yeah, it should be.
Like Arduino or USB or something. It's always something on Google.
Data sheet. Actually, come to think of it, I'm not sure. Does anyone know? Is the anti-aliasing built into your off-the-shelf ADC? Oh, this is really embarrassing. We should all know this.
I know, because we always just rely on them not being high frequencies to alias into it.
Yeah. Maybe you're...
Most microcontrollers do not have a low pass filter built in.
Right, okay, well, you've got to do it then. You've got to do it. Or else you can just make sure you use a signal chain that's inherently anti-aliasing. It's just about limiting bandwidth. Well, yeah, okay.
Usually when we sample, we don't have high powers at high frequencies, so probably there is aliasing, but it's so small.
Yeah. It depends. Anyway. Okay. So, anti-aliasing filters. So we got to do an active filter, and the reason we want to do active filters is that we if you want if you want to make a high order filter with complex poles, we need to have capacitors and inductors, and nobody likes inductors. So they're not good components. So if we can get rid of the inductors, then we can do whatever filter we like. But we need to have a gain element instead. Anyway, so the GMC filters is filters that is made from transconductors. So GM. So we have I out here equal to GM times V in, and capacitors. See, hence GMC filters. I should say two things. So this is this transconductor here is not operational. So we need to have a linear transconductor here. So we can't use the circuit we already used. The other thing I should say is that it is convention when you look at transconductors like that to define the current being positive when it flows out. is actually also the case when we look at operational transconductors, because if you don't do it like that, when you start to make negative feedback and stuff, it goes the wrong way around. So this is just something to keep an eye out. Always make sure you know which way the...
Isn't that how we usually do it? Because there's like a source inside, and usually the arrow points out through the series.
So if you look at the convention for current, they have defined positive flowing into the device. For everything. For everything, yeah. Yeah, but that's not, it's just inconvenient because it messes with the signs in your head, and you're going to make positive feedback if you don't define it like this properly.
And you're going to cover those ones in the program.
Yes. Okay. All right. So let's say we can make a GMC filter. All right. So what we could do is to have something like this. Oh, okay. So let me just, sorry, I should write, this got to be linear. Okay, right. So here, an input voltage, and then we can put a capacitor here, C, and that could be an output voltage. Okay, so transconductance GM. So the current that flows in this is going to be V in times GM. Yeah? So the output voltage is going to be equal to the current that flows in that capacitor times the impedance. So that's going to be V in times, sorry, it's capital GM. Oops. Times GM times the impedance of the capacitor, which is 1 on SC. So this is an integrator. Yeah? That is easy. We can make it into a low-pass filter by putting a GM load on. So if you look at GM1 there, and we put a capacitor here, and then we also put a transconductance here. So now it comes into the arm. So if I define the current flowing the other way positive, I've got to swap plus and minus, and now it looks like I have positive feedback. Okay? So this is just nicer, right, in terms of conventions. So if you look at what we have here, GM2, well, the current that flows here, that's GM1 times V in, and the current that flows here is, so what is that? The current that flows there is minus V out, so there's still V out. Right? So there's a, if this is negative here, if V out is negative, we have current flowing. We have current flowing this way out here. Yeah? So that means that that's going to be minus V out times GM2. Okay, and the sum of those two currents is going to flow in the capacitor. So we have that the output voltage is then going to be equal to 1 on SC times the sum of those two currents, so GM1 times V in minus V out times GM2. Okay, so what have we got there? We got on the left-hand side, or maybe I multiply through by 1, by SC here. So I got SC V out, so from that one there, and then I move the other V out onto the other side, so it's going to be plus GM2. So I've got this many V out, and what's left on the other side is GM1 times V in Okay, so the transfer function now is V out on V in. So that will be GM1 divided by SC plus GM2. I probably prefer to write this as taking GM1 divided by GM2 outside, because then I have 1 plus SC on GM1. Like that, is that right? No, that's not right, GM2. So, please complain when I make errors, because I will. Was that? That was a test. Yeah. Okay. So what you can see now is a low-pass filter, yeah? So you can control it easy again by the raise of those GMs. And you can, by GM2 and the capacitor, you can place the pole frequency where you want. Yeah? So first a low-pass filter. And we can continue doing that. We can really build anything that we like out of transconductors and capacitors, like that, any sort of filter function. Yeah. I probably would like to, if you know me, this is one of my favorites. Well, you'll see why it is in a sec. So what we can do, if we have a couple of transconductors, whoops. So we have GM. We can just make all of them the same. They don't have to be, but have a transconductor there, and then we pop that into a capacitor to ground. So C here, and then what we do is we look at the voltage, and we feed that into a transconductor like that. Plus minus, that goes to ground. So that would have to be going up here. Okay, now that it goes up there kind of should be obvious, because if I want to do a feedback loop now, I've got to make sure that any loops I have negative feedback, otherwise it'll not be stable. So I have 1 minus and 1 plus, so that's an odd number of minuses I've got to have around the loop. I also want to pop this into a transconductor that goes the other way. So like this, minus there, plus there. And then I have to put that up there, same argument. So these are all value of GM. Okay, so what do you have? The voltage here. That is going to be GM divided by SC. Okay, now that means that the current that flows there, that is going to be the voltage here times GM. Yeah, so that current is GM squared divided by SC, and that current there sorry, I'm missing an input voltage here, sorry. This is V in, so I've got to multiply that by V in, sorry. So I've got to have V in here. Okay, and the current that flows up here is also GM squared times V in divided by SC. So, so now we can see that what happens at the input side here is that the current is the integral of the voltage. So if you have a component in which the current is the integral of the voltage, well, what do we call that component? An inductor. Oh, isn't that fantastic? So this looks like an inductor. And this is actually looks like a floating inductor here, where we have so what if an inductor I have V equal SL times I. Yeah? So that's the inductor equation. So that means that the S divided by an equivalent inductance of of C divided by GM squared is what I have there. Is that right? I think so. Yeah, that's very handy. Now, if we have that, we can now. I mean, there's two ways we can make active filters, as you might know. So either we can construct them directly from differential equations, or we can substitute a simulated inductor into a sort of a passive filter structure, if you like. So either will do. So now we can have well, you know, complex poles and whatnot we want to have in a filter. So, yeah.
When then you need to use an inductor again?
Yeah, it depends on what it is that you want to do. So you might not have to. So when do you need to use inductors? You need to use inductors if you're doing power circuits where you actually store energy in the inductor. That's an important part. So a switch mode power supply, for instance. As a DC-DC converter, that's where you have to do that.
So would this operate the same and restore all the power in that capacitor?
No, because this is, you know, you have to, you spend power in order to get the differential equation. Yeah? So it doesn't work as an energy storage element like that. Can't do that, unfortunately.
This isn't like linear everywhere.
No, it's not linear everywhere, but nothing is, you know, not even inductors. So a physical inductor might have better linearity, that is true, but only up to a point. The other use case for real inductors is that if the frequency is really fast, because you know these active circuit has a finite operating frequency, and you need to be much lower frequency than the transition frequency for the transistors. And if you want to do RF circuits or something that's high frequency, you can't do that either. So, so those are the two use cases for inductors: so power switching, or power circuits, or a high frequency. Yeah. But on-chip inductors are not very good. You know, they are worse than discrete inductors. So the sort of best on-chip inductors you can have might have a Q of, I don't know, 30 or 40 or something like that, what is not good. And that depends on the process. And you know, you can get, it's not uncommon to do that in a modern process because they specifically make the top metal really, really thick, like 3 microns or something like that, even thicker, so you can get so the resistance that you get in the top metal is not too low, but still they're very big components as well. So 10 nanohenry is probably about as much as you can squeeze in with a with a Q of say 30 or something. So you can normally get, if it's not high frequency, you can normally get better circuits like this. Anyway, how are we going for time? Oh, pretty good. Yeah. Okay, I could show how to use this in a circuit, but you know, I think I'll just skip that. This is it's just a curiosity. All right. So probably the next thing I should talk about is how to make fully differential filters. fully differential GMC filters. Okay. Now, we already talked about why fully differential is good. So, how do you make a fully differential GMC filter? Well, it's very similar to fully differential op-amp. You probably also need to have a common mode feedback for each device sitting in there. But if you look at how to transform your transfer function, if you're building your circuit and finding the transfer function that you want, then you might probably do it using single-ended structure because it's just easier to draw. So if you have, say, the integrator here, like that, the current there, GM times Vn, and the capacitor C here, you want it into a fully differential circuit. What you really want then is that you have now the input voltage is between, well, it's still between the two inputs, but one of them is not grounded. What you have at the output then is then going to probably look like that. So capacitors in both these nodes here to ground. Let's make them both C. And then the output voltage now, actually got to look this way here. That's the out. And if you want to make sure that the transfer function is the same, we need to choose the transconductance for that one there, such that when we have the same input voltage here and here, we get the same output voltage here as well. Yeah? Now, because if we are injecting current into that node and we are subtracting current into that node there, the output voltage is kind of naturally, if you like, twice as big here than it is here. So we want to make sure that the current flowing out here is half of the current flowing out here. So we only have half the voltage change here because we'll get minus half the voltage change over there. So depending on how you define it, we want to have that current there being 1/2 times GMV in, and that current there being 1/2 times GMV in. Now, if you look at the difference between these two currents, okay, that is going to be that current minus that current. So it's going to be twice as big. So the differential transconductance here has to be the same as the transconductance up here. So let's call it IO minus, and this one here is IO plus. So IO plus minus IO minus is going to be the differential transconductance times V in, and you want the that differential transconductance equal to GM. If you define it like that. So if you define it single-endedly to each of them, then you get the you've got a half the transconductance. The other thing you can do, of course, is that you can keep these sort of single-ended transconductance the same, but make the capacitors bigger. So you get the same transfer function as well. So there's a few different ways you can do that. Yeah. Yep. Sometimes what you do is, in order to save capacitance, instead of having single-ended capacitance to ground here, you put a capacitance in between the two nodes here. And if you put it, but really at the moment, these two capacitors kind of sits between the two nodes because they're both connected at this point here. So it's like having a capacitance between the two nodes where the midpoint is at ground, which means for purely differential signals, these two capacitors really sit in series. So what you could do is you could, if you wanted to, you could make a different option here, where you put the capacitors in between here. So this would now have to be half C, and these still the same here. That's what we had before. So this would be equivalent. Might be an advantage because you can save capacitance if you do that. Yeah. And capacitance can be big and expensive. So, but if you do that, then if there's a common mode feedback and you're relying on that capacitance for stability, it's not going to help you common mode, as we talked about for the op-amps. Okay. So this is really the fully differential type of transconductors. There's a simple process you can follow if you have a single-ended filter and you want to make it into a fully differential filter. And I'll show it to you. So what you do is, let's have the low-pass filter we have up here. So that low-pass filter there. So single-ended to fully diff. Okay, so you start with the single-ended filter. Like this. Actually, I'll put another capacitor in just to make it a bit more complicated. So V in here, and then we have the load sitting here. Now, it is required that all your transconductors, for the easiest way, that they're all having one input to ground. And often they do, but in the inductor we used before, not all of them had one input to ground. In which case you need a differential type of transconductor. We're just putting more output. It's not a drama. But if you have if you can arrange your filter such that for all your transconductors you have one grounded potential, then what you can do is you can mirror the circuit in ground. And swap all the plus and minuses on the transconductor. So ground, and you mirror it in ground. And if you do that, then we have a circuit which looks like this. I call it C1, C2, GM1, GM2. Okay, and then we have C2 there, C1.
What's the role of the positive feedback C1?
So that C1, it's just another filter. It puts in a 0 in the transfer function. So yeah, if you have, if the current flows, in that, or it puts in a parallel path, so it becomes so you got current flowing both in this way here and also out there, so it adds extra current, but it would become a 0 in the transfer function. So it's just,
Is it for stability?
it's just because it changes the transfer function. So it's just a filter with whatever term. Sometimes you need zeros, and that will give you 0. So, yeah, okay. So that is the example like that. So this is V in and V out. Okay, so this is our mirror. So you can see this is actually, it's identical. Now I have swapped plus and minuses on all of the inputs and outputs, which means I have done nothing. Change the output to minus and swap these two, then it's just a sign convention for that. But with the mirror circuit, now what you can do is you can then merge, you can identify all these transconductors, and you can make these two into a fully differential one, where this is a positive input and this is a negative input, and that then becomes your fully differential structure. So mirror that, and then what you want to do is to merge. Okay, so then you will get a system which looks like that. So we can designate this to V in minus and V out minus if you like. So now we have a fully differential transconductor here. So we have C1 would sit across here. So well, hang on, did I do that wrong? I did, sorry. I didn't do this one here correct. It should be plus there and minus there. Yeah, got to swap them around. Oh, didn't do that right in the other one either. Oh, crap. That should be minus there and plus there. There we go. So now they are identical. So, so really this is a fully differential circuit. We just have a pass for the positive pass and we have a pass for the negative pass. But we don't really want to do that. It doesn't have the good properties of a fully differential circuit because we have the whole processing going in 2 different channels essentially. What we really wanted to have is common mode rejection in every single stage. We don't really have that here. So that's why we want to merge these two into one circuit, and that has common mode rejection in itself. So now we should be able to do it. So this goes from the top channel goes from plus, from plus to plus and minus to minus. So this was C1 here, and then we have another C1 going here. And this now be in. And then we have C2 going like that to ground. And then we have the load transconductor here. So we should have minus and plus, plus and minus. And so we should have still negative feedback around this one here, otherwise we've done something wrong. And this would now be the output voltage here. Okay. And the differential transconductance has got to be the same as the transconductance up here. But now it's a fully differential circuit, fully differential filter. So, yeah. I mean, you can really do this in any sort of filter chain that you have. It doesn't have to be a transconductance C filter. It could be an AD converter. It could be a GMC filter, or a switch capacitor filter. I'm going to have a look at later. So, yeah. Yeah. If it's fully differential, if there's no feedback in the common mode, then you've got to make sure that the common mode is stable. So you've got to have common mode feedback. So, as a general rule, you need to have common mode feedback in fully differential circuits. There are exceptions to that rule, and in some circuits the common mode is defined in the circuit structure. I can show you a fully differential circuit where the common mode is well defined. So Vn plus, Vn minus, V out minus, V out plus. Okay, so this one here you don't need it because the common mode is defined by these resistors. They fix it. Yeah. The trouble is that very often when you make gain structures, you have two current mirrors. To have high gain, you need a very high impedance, so you use active loads. So you have a current source and a current sink meeting in a node. And that, if there's a slight difference in the output impedance, that's just, you don't know where it sits. Whereas this one here, you do. You don't get a lot of gain, because you don't have that really high output impedance, but you don't need a common mode feedback now. So there are exceptions, and you can build circuit around that. But if you do this, it's harder to have high gain because...
And also the continuity fixed, right? Because like the more current we draw through, the more voltage drop there.
Yeah. No, you've got to... Yeah, you can't separate your gain from your common mode, for instance. Yeah, that's right. But they will be defined. So, yeah. So I guess that's the... That's rule number one of circuit design, know your bias point. Okay? That should be the first thing you ever do. Always, no exceptions. Okay. I'm going over time. I think it's probably... Is there any other questions to these structures? Say again? Can we match the capacitor? Yes, matching it. Or merge it. Yeah, you can do that. Yeah. So you in this one here, you could put a capacitor in between here if you want. Not with these ones here, but with the one that sits to ground, you can just merge them. Yeah, absolutely. Yeah.
C1, the waveform is a positive feedback?
Well, it does actually. That is true. It's okay to have positive feedback if you don't have too much. But you can work out the transfer function, and it should be I don't know if I worked it out. Yeah.
Because the capacitor actually contributes to the phase shift.
It does. Yeah. It introduces a zero in the transfer function. Yeah.
So they're not strictly like how 100 phase shift.
Yeah. So for very high frequencies, the impedance of the capacitor of these capacitors are dominating over the impedance of the transconductance. So the transfer function from here to here is just going to be the capacitor division you have between those two, which is another way to look at. There must be a zero sitting in there. So it'll be, So the other one was a low pass filter where the gain drops the time like that, and this will go out and be constant at some point, because at high frequencies we can kind of ignore these ones here. That's just to the output node. So that's a zero sitting in the transfer function. Yeah. Okay. Other questions? Yep.
Design-wise, how do you actually choose capacitor C1 and C2?
How do you choose the capacitors? So probably what you want to do is that you want to choose your transfer function. Yeah? So if we go back to this one here, so this is a very typical application that you want to a low pass filter what comes in there before you sample it. Then you will probably know what your sampling frequency is, and then you might know how many bits you have in ADC, and then you can work out, maybe you know something about the input, what do you need to fill out. So you can work out how much attenuation do I need to have for anything being folded back into the signal band. Now with that, you can then choose the pole and the order of the filter. Yeah? So you might choose, if you sample at 1 megahertz, you might want to choose that frequency there to sit, well below the Nyquist rate, so maybe sitting it at, I don't know, 200 kilohertz or something like that. Yeah, depending on how greedy you are. And if you say 200 kilohertz, still quite greedy, so you need to have more than a first order filter. You probably want to have, a second order or fourth order filter, so you have a nice steep roll down. Yeah? So then, if you choose, let's say you choose a third order filter, you get 60 dB per decade. Then you can work out where should you put your poles in the filter, and then that gives you. It doesn't. All the numbers don't fall out, but you get ratios, because you will get something like this. The pole location is now a ratio between GM and C. Yeah? So you can have all these ratios, but essentially that will leave you within just one free dimension to choose. And then you just have to choose one of them. Say, I'll make that 1 picofarad, and then you can calculate all the other ones. Yeah? Does that make sense?
Yep.
Yeah.
If we have like a multiple pole to make the low frequency band very sharp, so these three filters should have no coupling capacity, right? Just isolate that. Otherwise, it become a whole system, and the whole will have
No coupling capacities between the stages.
Yeah,
Well, it depends on what do you know. If you put coupling capacitors in between the stages, you get a band pass.
I mean, it will make this, because this 3 poles should be set at the same frequency.
No. Not at the same frequency. No. If you have 3 poles, you probably want to put 1 in the real and then 2 complex conjugate, and they are not going to be necessarily the same frequency. It depends on what type of filter you want to have. If you want to have a constant phase filter, you want to have a maximum flat or whatever filter, that depends on how you locate the poles, but not at the same frequency. Normally you put them all, but perhaps 1 in the as complex conjugate pairs. So yeah.
So they have the same real components?
No. The way that if you put in the pole locations in so you'd normally put the poles round like that in the S-plane, like that. And depending on how if this is a low-pass filter, yeah? So if this one here sits on a circle, then it's a Butterworth filter, it's maximum flat. If it sits on an ellipsis, it's it's a Chebyshev filter. If it sits in some other, pattern, you can have different type of filters with different properties. But this is not this course. We just assume someone will tell us where to put the poles, and then we can put the poles. Possibly MATLAB. Okay. All right, let's have a break here, and then we'll look at how to implement the linear transconductors.
Not course related. I'm doing a lab over at UCID, teaching a lab, and they've got this circuit here, which is a bandpass filter. This is just a 2.5 volt offset, so the output swings from 0 to 5.
Okay.
They've got their high pass, they've got their low pass, they've got their gain. This is convoluted, but it's basically this. So this 2.5 volt node is here, but it seems like they're
That
missing.
doesn't go to your signal ground. Where's that? This is
It's like a virtual. It's like this is like a 2.5 volt. So
Isn't that one?
Yeah,
That's not that one.
exactly.
Ah.
And also, they don't. This are the low pass. That's not a low pass. I don't know what that is. It's like they don't have a low pass resistor. Anyway, I haven't found the circuit online. I've tasked my friends with the promising
So
chocolates.
where's that? So what is that, and what is what's the source and what's the source? Is that the course notes?
This is the lab notes.
Okay.
This circuit I think works, like it's made and it works. I'm not sure how the low pass. I haven't tested low pass. I tested the high pass. I'm simulating it now too, just for myself. And then this is just I've googled online. This is some tutorial or something. But like this is just the form I'm more used to, where like you see the high pass, you see the low pass, you see the gain. Anyway, there's real questions, but yeah, it's very very confusing. I should know this. This is enough.
Okay. Yeah. Do that.
I have a question about 4602, our design project. Well, it says we have to first scale down the input analog signal, but I have a question. What if our input analog signal have some like DC components, such as it is originally oscillating around the 2 volts? Do we have to filter out the DC component to process?
No. No fill out. What you do is you have to have, this is unambiguous. You have to linearly map that range there to that range. A linear map.
Because according to our design, there is a shift after our scale down.
Yes.
Yeah, but you see, if I scale down the
Okay. I'll write it to you. So this should not be ambiguous. So if you want to linearly map, you can swap it around. That's okay.
I was thinking about
You want to have V in. You scale that by 0.1, and you add 1 volt. That is what you have to implement.
that is exactly what I want to do.
Okay.
But it feels strange to me because it looks like we should be oscillating around 1 volts in the output.
Well, if that's that one there, so if this oscillates around 0, full scale, then the output will oscillate around 1 volt.
Yeah, but if the original signal is not oscillating around 0.
That doesn't matter. You still need to implement that.
Thanks a lot. Oh, sorry. The first question is that these 2 low and high voltage, is this for the VG?
Yeah.
Oh, thanks a lot. Thanks a lot.
I have a question for like a differential pair. If I wanted to add the signals before differentiating, I just like V1, V2 plus, V2 minus, V1 minus.
Yeah, you can do that. Yeah.
Yeah, because in the spec they want you to do things VAP minus VAN is greater than VBP minus VP, right? And you want to this was the assignment, right?
Yep.
But if you just switch the negatives, then it becomes a P
Yeah.
plus V.
Yeah. No, you
I
can
can
do
just
it.
use this.
You can, but that will not. So important. Any of these voltages can be within entire supply voltage, which means that that one there has to be done in a linear fashion.
Yeah.
Now, I don't know if you can make that linear. So
Even with, if I have both NMOS ones and PMOS ones, like the complementary pair, but now got doubled up, it still won't be linear on the edges. But basically, I've done the complementary like you showed.
yeah.
But I've done like that.
But still this this has a finite common range. So if you so the largest differential voltage you can have on that is when all of this current flow in one of these transistors.
Yeah.
And that depends on the, well, if it's in strong inversion, it's going to be like 2 effective voltages. I mean, it's a horrible equation with square roots and force powers and stuff, but you can work it out. So that will be your the range. So the transfer function for that pair looks like this. So I out 1 minus I out 2 and V1 minus V2. It looks like this.
And obviously on
And-
the it's not really linear.
Yeah, so you got to, and this sort of thing is, I can't remember, there might be, I don't know, square root 2 times the effective voltage or something like that. I don't know. It's some, as I said, it's a horrible equation, it's quite complicated, but you can work it out. Maybe you should, just for the exercise. Now that means that if you want to have a large linear range, and this is not linear up here, so that means that if you operate up here in one of them, and the other one is operating,
No, I mean, I know what you're saying. If any
Yeah.
of the voltages are too high or too low, you're going to have nonlinear.
yeah.
Even
So-
if you do complementary pairs, and even the complementary pairs just allows you to have a bigger range. It doesn't
Yeah.
make it
See,
linear.
I don't think you can do it like that, but I would love to be proven wrong. Yeah.
But my little.
Yeah, but you got to operate it at a high effective voltage, and you have high
The problem with
effective.
this is
Yeah,
it's just not linear. Like,
yeah.
but how do you make it linear? I guess you can make the voltage smaller.
That's what you got to do. You got to make it smaller. You got to make it
I've seen a
smaller.
thing on, like, are you talking about the MOS and PMOS pair, like only one of them turning on?
Oh, but that's even worse then. Because,
Well,
if only one of them's on and one of them's off, you're going to have more nonlinearity.
yeah, but yeah, I've seen a thing in a textbook where there's like some sort of feedback where when one of them turns on, it like shunts some extra current to one of the other pairs so that it increases their
That's like what you showed at the start, right?
transconductance.
When you
Yeah,
showed
I think
the-
he
When
mentioned.
you showed the complementary pair and how
Yeah.
you can change the biases.
You can. But
That
that
doesn't solve that.
no, it doesn't. It doesn't.
That just solves the issue.
Yeah. So you're still assuming that you're operating down here
Yeah, but
with small input voltages.
I was like, my initial impression without reading anything was, oh, if you just chuck the whole thing in negative feedback, then maybe that non-linearity won't be so bad. But then I read that like it can sometimes be so bad it just causes instability anyway. So I need to do research.
Yeah. Now maybe it's possible with feedback that you could, if you have feedback and you have 2 pairs, maybe. I mean, if you're sitting up here, your feedback stops, because you have no gain. So you essentially open loop your amplifier if you model up there. So you've got to be sure that you sit within that range.
Because how much gain does a preamplifier really need to have? I didn't think
It doesn't need to have.
It just needs to, yeah. So I was like, maybe if you like put a whole lot of negative feedback, maybe it won't be so bad. But I don't know.
So there's also, I can't remember who suggested it, but someone was talking about using switched capacitors as well as a means.
We haven't gone to that yet.
Switch
So,
capacitor.
yeah, because that,
I wish the non-linearity worked on both of them equally. So then when you compare it
yeah,
again,
well,
then it adds,
it's,
but I don't think they do.
yeah, well, I guess you just got to do the math, and
It's simple as, yeah, we are.
or perhaps do some simulations if you're a bit lazy, yeah. But,
Switch capacitor thing.
yeah.
I don't get the switch capacitor.
We'll find out when I do the presentation in an hour. I'll explain how that silly converter works.
Yeah. Okay, we should start again. Right. All right, let's start again. So, let's start with the differential pairs. So we want to have a circuit in which the output current is some kind of constant times the difference of the two input voltages. So what we have here in a differential pair, obviously, is we've got output currents here, and the drains, but it's not linear. It has a transfer function that looks something like that. So yeah, not linear. Now, the first thing you can do about that is you can, the easiest thing is that you put in some source degeneration resistance. This is your go-to method for linearizing a circuit. Yeah? So putting in some resistance here, get rid of some of these wires here, and then putting in some resistance here. Now, if we make sure we make this resistor large enough, then when the voltage across the gate source and this resistor here changes, then all of that voltage change should sit across the resistor. So really we want to have that resistance there being a lot larger than 1 on GM. So it's R there. So that should be much larger than 1 on GM.
Is this analogous to like when we put a series resistor with the
Yeah. Yep. It's exactly the same idea. Yeah. Now, if you look at that, then there's a common way that you change the bias here, because this is if you make this resistor large, then you get a large voltage drop across it in normal operation, and that's just eating up your power supply voltage for no reason. So typically what you do, if you then split the bias current, so we don't actually need to have DC current in these resistors, we just need them in the transistors. So you can route them around so the current flows. Let me just draw it again. So we've got the two resistors here. Let's call it 2R, like that. And then we have half the bias current here, and half the bias current over here. Like that. So this is essentially the same circuit, except that now if the two input voltages are the same, there's going to be 0 volts across the resistor, and all the bias current flows in that. So this has a better input range, just better.
If we're doing AC analysis, we tend to count sources into grounds rather than with 2 on
No. What do we do with current sources when we do? They go open circuit.
That makes sense now.
Yeah. Yeah, so that becomes the same. Yeah? It goes open circuit. Okay. So now what we have is essentially the, if we can satisfy that one there, when we have approximately across that V in V1 minus V in 2, there might be some DC voltage drop, but that doesn't actually matter. The voltage difference is still going to be appearing across the resistor, which means that the current here, that current is going to be V in 1 minus V in 2 divided by 2R, and that's the current that go this way and that way, small signal wise. And then what we do is we pop. Well, if you want to make a single-ended transconductor, then we want to subtract those two currents. Now we could subtract those two currents by putting a current mirror up here. It is more common to put that structure into something that looked like a current mirror op amp, because if we put just a current mirror up here, then the voltage restrictions that we get on that node is this has got to be in saturation, so this can't swing too low, and that's normally too restrictive. So typically we wrap that core transconductor sort of thing into a couple of current mirrors, probably with cascodes at the output, so we have a high output impedance. So that will look maybe like that. That. So now we have, we have those currents flowing this way here and that way there. So let's call that I1 and I2, which is the same. Yeah. So you've got I1 over there and I2 there. And then depending on whether we want to fully differential. Actually, let me just draw a single-ended one first. So,
what are you saying we did? What use current mirrors, or what was that referring to?
well, we don't want to have a current mirror sitting up here, sort of a current mirror between these two nodes, because then that becomes the output. And if that's the output node, then the output node is restricted in how it swings. Yeah, so we just mirror them around. That's common to do. So I'll show you two options on how to do that. So we can put so it's actually looking almost exactly like a current mirror op amp now. So I have two options. If I put a mirror in here, then this becomes I out flowing this way here, which is going to be, in that case, I1 plus I2. The other thing I can do is I can not have that, and then I have two outputs. I have a current that flows in here, which is I2, and a current that flows out there, which is I1. And these are the same, but they flow in different directions, and they are now half the size. So now that kind of automatically, whether I put this connection or not, I put it in, I get a single-ended transconductor. If I take it out, I get a differential transconductor where the differential transconductance is the same as what I had before. So I need to have common mode feedback if it's differential, obviously, and all that sort of jazz. Yeah. And I probably want to put cascodes on at the output. But now the output voltage can have a large swing, and we just need to keep these ones here in saturation so it can swing almost the entire power supply. Whereas that's not the case if we make that one there the output.
I think we covered this last week. What's the difference between this and a telescopic? So the telescopic has a reduced swing, but what's the downside of this compared to a telescopic? Because it still seems like there's only one.
Oh, this is actually still a telescope. If you put cascodes in here, that will be a telescopic cascode. You can also wrap it into a folded cascode.
Yeah.
That is perfectly fine. So you can take these two output here, just as you want, do if you implement a folded cascode amplifier. You have a differential pair with two outputs you stick into the folded cascode structure. You just do the same. The only difference is that you have linearized the diff pair. That's the only difference.
It just seems to look different. Like I've come across these ones where the current you can sort of wrap around it as a single-ended.
You have put in a cascode on top of the differential pair there. Yeah, that is very restricted in voltage swing.
Yeah.
Yeah. You can do that, but only if you're sure that the output voltage doesn't need to be smaller than the input voltage.
Benefits to this then versus that?
You have, this is probably faster. Okay, let me just, for the sake of the class, just show what you have here. So you have.
Because I think we covered this.
No, we did. I didn't do this, but this is.
We sort of started with the classic telescopic, which is what you're drawing now, and then we moved on to the one that we're just covering. Because I've seen them both in like papers and textbooks when they refer to OTA.
Yeah.
They still seem different from like a normal two-stage amplifier or something.
So, sorry for the quick drawing here. So that structure there. So this uses up a lot of voltage here because you need to make sure that all of these are in saturation. This is not trivial to do. Now the first thing is you've got to, if you want to maximize the voltage swing, you've got to actually change the bias voltage for the cascode here with the input voltage. Right? So you need to kind of track that for that. It's not a constant. Now this voltage here cannot drop below 2 effective voltages across here. Yeah? So that means that if the input voltage goes up, you kind of have to restrict what the output voltage is doing there. And sometimes that is fine if you're making an amplifier in one of these super cascodes, whatever, where you have a very restricted voltage swing at the output, you know exactly what it's going to be, what the DC value is going to be. That's okay. That's fine. And this is good now because you don't have these extra current mirrors that make this faster. Yeah? And it also makes it lower power because we don't have these extra branches where the current flows in. But the output voltage range is crap. Yeah? So in general, for general use components, that is not acceptable. And then you essentially gotta wrap the output away from the input pair in order to separate the voltage swing at the output and the input. Yeah.
You said that resistor made it more linear. How much more linear?
Well,
that graph you put on the board, like you're seeing that past like square root 2 VF.
yeah.
It's very non-linear, but what about this one?
Well, it depends on how much better you do with this one here. This is up to you. Okay, so you can make R 100 times bigger than 1 on GM, then the amount of the GM changes is going to be a fraction of a percent probably, for most cases, but yeah. So you can do what you like there. And if you want to make it even more linear, then what you can do is you can pop in an extra amplifier stage here. So if we, purple. Okay, so I'm just moving this away here, over there. Okay, so if you put in like that, okay, now I don't really need to worry so much about that, because the GM, the effective GM when I put an amplifier from the source to the gate like that is going to be increased by the gain of that amplifier. So now this is easy to meet, which means that I can pretty much ignore that, and I have a very nice and linear circuit here. This is probably going to be limited by the linearity of this resistor. Yeah, so this is very good, very nice and linear now.
The power draw would be quite a bit more.
The power draw would be more because you have to. So these amplifiers are not complicated. Okay, so this is probably if you can get away with it, this would be an amplifier of this type, but probably without the cascades. Yeah, so just a differential pair with a current load. You need to make sure that your input range is still really important to have there. But when you do that with a current load, you don't need to have freedom between choosing the output voltage and the input voltage, because it's a voltage follower. So you got to make sure that it's biased properly, but they follow. So you don't need to have that extra freedom. So that is common to do in these sort of little helping amplifiers. You don't want them to be complex, because then you get more poles and then you slow the circuit down enormously. So they've got to be fast. Yeah. And just a bit of gain is fine. Yeah. So yeah. So these are really the core probably the most common way to make a linear transconductor is by wrapping a resistor around a circuit and applying the input voltage across that and sense a current in it, and then route that out.
Sorry, before we move on, I know we're both confused. With the equation book above, that RE had to be much greater than 1 on GM. But now you're saying we're increasing 1 on GM by the gain. So doesn't that mean we need to make R even bigger so it's still dominant?
No, I'm increasing GM, not 1 on GM. I'm increasing GM. Yeah.
And what's the benefit about being small?
Well, you want to meet this. Yeah. So this is a source resistance. If I make this one here bigger, then this equation is easier to meet.
And does that makes it more? Does it mean small resistor for better linearity?
Yeah.
And are we going to cover how to do this without using resistors? Like if we want to do something like low noise or something?
I'm not sure low noise is really something that is better without resistors. So the alternative is to use a transistor instead of a resistor, but a transistor probably have more noise than a resistor. There's more noises.
Amplifying one, we could use a small resistor anyway.
Yeah. But what you can do is you can, if you look at the resistor here in your diff pair, like that, you can turn it in. You can replace it with a transistor actually. So the current source is in there. Like that. And you operate that in a linear region. So in the bias condition, there's going to be a zero drain source voltage across that. Now, if you if you have a circuit where you apply a fully differential voltage at the input as you control a common mode, then this is actually a linear circuit if it's in a triad region and strong inversion.
As long as V isn't too big to get into saturation.
Yes, it needs to operate in triad region. As long as it's in the triad region, this is linear. The difference in the two current at the output is going to be a linear function in the voltage difference at the input. Let me just, I really don't think I have time to prove it, but okay, I should write like this. Okay, so if you apply a fully differential signal, so half Vd plus the common mode for each of these, you might wrap it around, you know, with the op amp. If this is applied across here, then we have the triad equation for the transistor. So we have the drain current is equal to mu Cox W on L times VGS minus the threshold times VDS minus a half VDS squared. Now, if you are if you're putting in for the gate voltage and the drain voltage and the source voltage into here, then what you'll find is that it becomes linear. It will depend on the difference between the bias voltage and the common mode voltage, but that means that what you can actually do with a structure like that is that you can control the transconductance, which is neat. Yeah? You can change the bias voltage and that changes the transconductance. You can't do that with a resistor. So, have I written down what the? I think the resistance becomes. I think it's become mu Cox. No. There we go. So it becomes mu Cox W on L times VB minus the common mode voltage minus the threshold voltage. Okay. So that's the result. So this is tunable. That's not hard to prove, but I'll leave it there. Yeah. Okay. All right. There's other ways. Yep. Would it be better to use a transmission guide? Yeah, so it is. So the right-hand solution there is restricted in the voltage you can apply at the input because it needs to be in a triad region. Yeah. So can you put in a transmission gate? So you suppose a P and the N in parallel in order to extend that range. I don't think so. I don't think so because if you want this to be linear, you have to apply a fully differential voltage across it. Otherwise, it's not linear. Okay, so if you look at the difference current, it's a fully differential mean, and that means that you are not really by putting in the P device, you're not really gaining anything because you will have the same drain source voltages in both of them. And they both have to be in saturation. So I don't think it helps. In the triad region, yeah. I don't think it helps. In fact, I think might even make it more restrictive because you need to make sure that both the transistors would be in the triad region. So I don't think it'll help. Yeah. It's a good question though, because sometimes transmission gates are better than single transistors. Yeah. Okay. Anyway, we can make it tunable. Yeah. All right. There are other ways you can do that. Yeah. Okay. I should probably not have too many different. Yeah.
Would it be like, so because the current can be differential across that triode transistor, would it like kind of not make sense to think of one of the terminals as the source and one as the drain, so they both sort of swap depending on the direction of the current?
Well, the way that you normally define the equations is for an N transistor is that the terminal with the higher voltage is the drain.
But then, like, depending on which way the current goes, one of them can be higher than the other, right?
Yeah, it will be. Yeah.
Okay. So then, okay.
So what is a drain shift like that?
So is that like a okay?
Yeah, it doesn't matter. It doesn't matter.
Whenever we do our B curves, we never do BDS going around it.
Uh,
Is it just mirror? Does it go?
no, because it never happens, because you define the drain in an NMOS transistor as a terminal with the highest voltage.
Or tying the bulk to something?
If you're tying the bulk to a voltage which is not, to something which is not your negative power supply, it is still technically true that the terminal with the highest voltage is a drain. Even if you tie the bulk to...
But our bulk isn't tied to the source of the drain, it's just tied to the power supply.
Yeah, but it'll still be true that it'll still be, that's just the definition of how you define it. Now, if the bulk is tied to higher voltage than the source, you might forward bias the diode, but that doesn't change what is the source and the drain. Yeah.
And for simulation purposes, though, they only, like the MOSFET kind of has a defined drain and source, right? Like the signal has a...
The symbol has a defined drain and source, but the model in the simulator is symmetrical. It doesn't matter.
Okay.
Yeah.
Well, I mean, that makes sense.
Yeah. So, yeah, it's completely symmetrical device. Okay. Okay, so let me just show you one last way that you can make a linear transconductor. So this is essentially by means of cancelling nonlinearity. So one way you can do this is by having a differential pair like so, and then what you do is you pop on another differential pair branch. There's a number of different ways you can do this. So you put a voltage source in series with this, so they have a constant difference in gate source voltage. Pop it in there, and this one here has a minus plus there. Let's call that VB and VB over here. And then what you do is you cross couple these ones here. And this is your your bias current, ISS or something like that. And then this is V1 and V2, and we look at I1 and I2. Okay. Now, if these transistors are all in strong inversion, and they follow the square law, then this becomes a linear circuit. And the difference. It is not very easy to, very difficult to prove. If you look at the voltage there, then we can find the gate source voltage here. So VGS1 is equal to V1 minus Vx. We can find VGS2, that one there, VGS2. So that will be V1 minus VB minus Vx. We can find the same as on the other side, and then we can find out using the drain equation is 1/2 mu Cox W on L times VGS minus the threshold voltage, square like that. We can now find that I1 minus I2 is going to be equal to mu Cox W on L times VB times V1 minus V2, like that. So this is from this is the simplification, I guess. So this is the current, which is obviously not completely true, but if this is true, then that is true there, and they're all in saturation. So it completely cancels the nonlinearity. There's a lot of different circuits, a lot really, which uses a very sort of similar approach that you might know the equations, and then you can cancel nonlinearities by having a number of different differential pairs that are biased with different currents or different voltages, and you add and subtract them. And you can keep going, to get second order and third order effect cancels. Well, you can also do it by bipolar in sub-threshold, if you like, where you have an exponential function. It doesn't cancel out as neatly as that, but you can cancel it out to the order that it pleases you by just adding differential pairs like that. Again, the advantage of this is that you can control the transconductance by controlling the bias voltage. So this is something you can do in a calibration phase, for instance. You can hook it up to a phase-lock loop or something like that and drive that voltage, so you don't actually need to have a manual calibration phase for that. So this is handy. You can drive that voltage. It is admittedly that is a floating voltage source, which is which you've got to make. But yeah, so you have some restrictions on what you can do. The simplest way is to use a source follower for that to get a constant voltage across them. But yeah, that's in general not trivial to make a floating voltage source. But
I feel like we don't come across this often. It seems really useful.
It is useful. It is useful.
Is it super common? I feel like I've never come across something like that in any sort of op-amp papers. Well, because I guess we always have, in like a 741 op-amp, there's always external feedback.
Yes. So for discrete, it does rely on, okay, so the other thing it relies on is that all the transistors have to be identical. Yeah, so it's not something that you find in discrete circuits, but you do find discrete circuits that you can buy that has maybe that function in it, for instance. Right.
Discrete circuits in any of the op-amps that we commonly use,
Transconductor filters might be something that you find, but quite typically for the filters that you want, it's not very common that you have a filter. If you look at a chip and you have a filter chip, it's not very common that the filter chip has a predefined cutoff frequency. So it'd be more common that you can control a cutoff frequency in some way. You normally do that with external components, and that's kind of where the trimming come in some fashion. Yeah. Okay.
I think that actually this circuit will consume a lot of power, especially VP using a source follower to implement it. Because the effective voltage for the VGS one will be pretty big.
Will it consume a lot of power?
A lot of current, right?
A lot of current. You have a number of branches, yeah. So if you put source followers in for the bias voltage, then you have 3 branches of current. But how much?
So the VP will become a VGS, and the effective
Yeah. Well, whatever you do, you can't make anything without consuming current, as a general rule. It's very rare that you can build some function in that doesn't have static power being dissipated. So it's not necessarily more than what you have in some of the other circuits, or not appreciably more. I mean, if for instance you do, if you can get away with doing something like that, that uses less current than if you do this, yeah, because this uses twice as much current, if you're not doing any scaling. And this is a price that you pay for having that extra voltage range, because nothing is free. Yeah. So I don't think it's necessarily a problem that it uses more power, but it will, because you have an extra branch sitting in there. All right, I think that's all I want to do for continuous time filters. So we've got to have a look at the other type of filters today. So we've got about half an hour left for that. So this is switched capacitor filters. Okay, so let's first look at a switched capacitor. So if we have a capacitor here, and we have 2 switches, and when we switch these ones here, we normally have 2 clock phases, 2 non-overlapping clock phases, often called phi 1 and phi 2. And phi 1 would go something like that, and phi 2 would go something like that. So there's a non-overlap period here. And then we look at what happens at the end of phi 1. Let's call that time nt. And this would be n plus 1 t, where this is the clock period. This one here, at the end of clock phase 2, this would be n plus a half t. Yeah? So that's what we kind of always do in these sort of switched circuits. Now, if we look at applying a voltage here and another voltage here, then we can see at the end of clock phase 2, the voltage across the capacitor here has been switched to V2. That's been charged up to V2. Okay, so when we then go and switch in clock phase 1, we will have a charge that flows into that capacitor, which is this voltage here, V1 minus the initial voltage V2, and then times the capacitor. And that is a charge that flows in there. So we've got a charge in here. Q, which is equal to V1 minus V2 times C. Now, if we assume, just for, yep?
I was going to ask, are you assuming that the clock is on long enough to charge the capacitor fully?
Yes, I am assuming that, yeah. Yes, this is the normal assumption, completely discharged. So if you look at the voltage on the capacitor, that's a good point. So VC would then look like on the time here, we see it'll probably go
Do we go to 90%, or is there like a fixed point that we charge to?
completely settled. I don't know. I mean, you make an error in because we can't let it complete a cycle. It's like an exponential. Yeah? So how long is a piece of string? Yeah? So, but
We cascade, we've got a lot of switching things.
what you really got to think about is depending on what you make with these circuits, how accurate do you need to do your signal processing? So you can build an ADC out of these, for instance, and if you do that and you want to have 10 bits, you need to make sure that settling that you have there, the error on the settling, is much smaller than 1 LSB. So that might be, let's say a quarter of an LSB or something like that. So you've got to have the time constants times log to 2048. No, 4096. What is, I don't know, 8 time constants or 7 time constants or something like that. But it depends. Yeah. All right. So for the purpose of analyzing, it's just settled close enough. Okay. All right. Okay. So if you look at what happens then in the next clock phase, so this is then during, that's phi 1. So during clock phase 2. Phi 2, then we'll have a charge flowing out here, Q, which is going to be the same as going to be, assuming V1 was higher, for instance, then that charge will flow that way, and it's going to be discharged to V2. Same charge change we have. So it's going to be equal to V1 minus V2 times C. So in either case, it's the same charge. So that means that we can actually see that the current that flows in here, the average current that flows through this structure here, well, that is going to be that charge divided by the clock period, like that. So this is going to be equal to C on T times V1 minus V2. So you can see that from an average perspective, the current that flows in that is proportional to the voltage across it. Now, what is that called? It's a resistor. So it looks like a resistor from the average point of view. Anyway. And the equivalent resistance that we have is the equivalent resistance is then going to be T on C. Normally, you write that as the clock frequency times C like that, where obviously the clock period is 1 divided by the clock frequency, like that. Yeah. So if you switch it fast, it looks like a small resistor. If you use a big capacitor, it looks like a small resistor. Okay. Now what we can do now is we can say, oh, that's a resistor. Let's make an active integrator. Now, how do you make an integrator? Well, we can do it like this. That's your simplest integrator. And then if we don't use a resistor, but we use a switched capacitor instead, then that then becomes your switched capacitor. So clock phase 1, C1 there to ground, clock phase 2, and then we have the op amp. C2 here. Okay, so here we have what is the transfer function of this one here? This is the in, the out. So this is 1 on C SRC times Vn. Yeah? That's a transfer function, oh, with a minus on, sorry. So what we have down here for low frequencies, we have V in, V out. So this is approximately equal to -1 divided by S times the equivalent resistance, which was that one there. So this is 1 on the clock frequency times C1 times C2, like that. The end. So yeah. So what is that? So this is equal to minus F clock times C1 divided by S times C2. Okay. So, yep.
Tricky, but why is the charge transfer during why was the charge transfer the difference in the voltage? Like proportional to the V1 minus V2. If you scroll up a bit. Yeah. Well, why is that V1 minus V2?
Okay. So look at the capacitor here. So at the end of clock phase 2, this capacitor has been connected up to V2.
Yeah.
So the voltage across that is V2.
Yeah.
Now you connect that via a switch to V1. This has now to charge up to V1.
Yeah.
Right?
Okay.
So how much charge do we need to add to that? That's the voltage change times the value of the capacitance.
Okay.
Yeah? You happy?
So in the second stage, would it be a negative sign on the red?
Well, with this direction here is when V1 is larger than V2. So if V2 is larger than V1, then they will both flow in the other direction.
So I was just thinking, so the first one you went from V2 to V1, so the voltage difference became V1 minus V2. In the second case, you're going from V1 to V2.
Yeah, but what I did do though was this is positive this way and this is positive that way. You're thinking like that, yes, and then it should be symmetrical. Yeah, that's right. Yes, that's right. But that's because I knew the answer. I knew that they were going. It looks like current flowing this way here, so this makes more sense to define it like that. Yes, but you're right. Yeah.
So that Q is like a delta. It's a delta Q, right?
Oh, it's a delta Q. Yeah. It's delta Q.
So we were like shorting two voltages together.
You're shorting capacitor to two different voltage sources. Yeah.
Oh no, in the equation, the average current equation at the end, it was related to the period. So if you make the frequency really high, does that change the current?
Yeah, because every time you do one cycle, you get the same amount of charge. Yeah. So if you double the frequency and then you double the charge of flow for the same amount of time. Yeah. So this is why you get out of it is an equivalent resistance, which is inversely proportional to the capacitance and the clock frequency. So doubling clock frequency doubles current.
It's like we're climbing a ladder and two steps separate.
No, you're just doing it twice as fast.
Twice faster, exactly.
Yes.
It's the same step, same charge.
Yeah, that's right. When you make the capacitor bigger, you make the steps are further apart. Yeah. Okay. All right. Okay. So the reason that this is good is that hang on, what am I here? Okay. So if you look at the filter pole you get from this, we got a pole which is RC. Now, normally when we make filters, we know that the sampling frequency is given whatever, so we need to make our anti-aliasing filters, whatever frequency. So that's normally something we need to achieve with absolute accuracy. Now here we got 20% variation in both R and C probably, So this will give like a 40% variation in the location of the pole. Now we can still make a filter that has a high order because we have good matching, but we don't know exactly what the cutoff frequency is. However, if we look at what happens in the switch capacitor filter, then the filter pole location is depending on the ratio of two capacitors. And if that has an absolute variation of plus minus 20%, that probably doesn't matter because the ratio is going to be accurate. We have good matching between the capacitors. And if we can have an accurate clock frequency, and this is common, most systems, they use a crystal somewhere, so it's not unusual to assume you have an accurate clock frequency. We can put this pole pretty much exactly where we want it, maybe within 1% or less accuracy for that. So much more accurate. And this is one of the key reasons I might want to use it. So if you're buying an accurate filter chip, that'll be a switch capacitor circuit, even as a discrete component. Yeah.
Isn't this just like an origin pole?
An
origin pole?
origin pole?
Like output zero frequency, like DC?
Yeah, it's an integrated, yeah.
So then probably wouldn't go around much, right? Unless you add like...
You probably have some feedback around that, yeah, otherwise it'll saturate.
Is this typically pretty large? Could you do that on chip?
Pretty large.
The resistor you put in parallel with the capacitor at the top.
Yeah, isn't that usually like a pretty large resistor?
Well, it depends on where you want to put the pole. Yeah. This has, if you want to make it really low frequency, this, the continuous time is difficult to do because now you need to make a really large resistor and a really large capacitor. Now making a really large resistor here is easy. You just lower the clock frequency. So you can get much lower cutoff frequencies that are still accurate with this one here than that. Of course, this is now a discrete time system. So you can't use it as an anti-aliasing filter. But yeah. Okay. All right. Okay, so so this is a discrete time system. That means that me doing this one here is not correct analysis. So I've been really I've been really naughty because I put in a clock frequency and I use the S domain. It's like, actually, it's a bit. And this is okay as long as we're looking at frequencies here that is much slower than the clock frequency. That's okay. But if the frequencies are not much slower than the clock frequency, then we got to analyze it in a different way. So we got to look at what is the discrete time system. So the way to analyze this in discrete time is really to look at the charge transfer that you have. Okay, so like this. So let's try and see if we can analyze this one here a little bit better in discrete time. So I'm just going to take a copy of this. Copy. Paste. There we go. Yeah. Pop it up there. Okay, now what I do want to do, I want to look at the output of this at clock phase 1. I can also look at it at clock phase 2, but it is a discrete time system, and I will look at it in one of these two clock phases. So looking at the clock phase 1 makes it a little bit more intuitive to see what is happening. Okay. So let's see if we can analyze this. So at the end of clock phase 1, what have you got? We have the VC1, so VC1 of NT, so end of clock phase 1 was NT, so the end of that, or n plus 1t, whatever. End of the first clock phase 1, end of NT. Now this is going to be equal to the n at that time there. At the end of clock phase 1 as well, we will have a voltage across C2 there. Let me define the voltage across C2 like that. We have a voltage across C2, what is then going to be equal to the output voltage. Yeah? So the during clock phase 1, this is closed. We've got 0 volts here, so the voltage across C2 with that sign is equal to the output voltage. So as VC2 of NT, that is equal to V out of NT, like that. Okay. Now at the, now we open circuit all of these phase 1s, and see what's going to happen at the end of clock phase 2. And when we do that, end of clock phase 2, we short circuit that phi 2 there. Now we've got virtual ground and negative input, so this is going, C1 is going to be discharged. Okay. Now in order to charge that to 0, we've got to have a current flowing from the bottom up, this way here, and the charge of current flows up this way, and they can only flow into the capacitor in that direction. Okay, so if you look at end of clock phase 2, then VC1 at end of clock phase 2, so n plus a half. Let me just drop the t's. Do you mind? Oh, it's too much writing. Sorry, let's drop the capital T's there. So just V of NT is the same as V of N. Okay, otherwise it just becomes really cluttered. Okay, so VC1 of half a clock period is going to be 0 volts, and then we have VC2 of n plus a half. Well, we add charge to it, so it's going to be the voltage we had before, plus whatever charge that sort of flowing in that capacitor there. So it's going to be VC2 of n, and then let's see, it's going to be minus the charge that flows. So that's going to be VC1 of n, the one we had over here. It's going to be the voltage that used to be on VC1 times C1, and then divided by C2. Is that right? So the voltage change. Let's see. So the charge flows, if this is a positive voltage, we have charge physically flowing up here, and it's flowing from minus to plus. So it's going to reduce the voltage on that capacitor. Okay? And the charge here is going to be the voltage times C1. So that's what we have there. And that charge here is going to create a voltage change here, which is going to be that charge divided by C2. So that should be correct. Okay? All right. Now what we can also see is that at the end of clock phase 2, we have that. At the end of clock phase 1, we're not changing any voltage across that capacitor there, because clock phase 2 go open circuit, there's no current pass in that. So at the next clock phase 1 again, we have Vc1 of n plus 1 is going to be equal to Vn of n plus 1, but also Vc2 of n plus 1 is going to be equal to Vc2 of n plus a half, which is equal to Vc2 of n minus C1 on C2 times Vc1 of n. Now Vc1 of n was equal to Vn of n, and Vc2 is equal to Vout of n. So I can now write this as Vc, so I can, instead of having Vc2, I can write Vout of n plus 1 equal to Vout of n. So this is this one and that one. And then minus C1 on C2 times Vc1 of n, which is V of n. Okay? All right. So the next thing I want to do is to do a set transform, because this is a discrete time system, and if you want to find a transfer function, we've got to see it in a frequency domain, which is a set transform. Yeah? So so if a time n plus 1 is now, then time n was 1 clock period ago. Okay? So this is now. So this is the output voltage delayed by 1 clock period, and the input voltage delayed by 1 clock period. Now, how do we do delay? We multiply by set to the minus first. Yeah? So we have set equal to e to the power of st, set to the minus first, 1 clock delay. Yeah? So we have Vout, so this is in a set domain, Vout equal to Vout times set to the minus first, minus C1 and C2 times Vin times set to the minus first. Okay, and now we can find the transfer function. So moving Vout onto the left hand side, we have 1 plus set to the minus first. Vout is equal to minus C1 on C2 times Vn times set to the minus first. So that means that Vout on Vn is equal to minus C1 on C2 times set to the minus first divided by 1 plus set to the minus first.
Should that be minus?
Yes, it should. Thank you very much. All these tests I give you, eh? Yes. Yeah, otherwise it's not inside the unit circle. Ooh, whoops, yeah. Okay. All right. Well, it's on the unit circle, I say, but yeah. Okay, so this is an integrator, yeah, with a 1 clock period delay. All right, so that's a correct analysis. But yeah, there we go. So basically, that process is probably, when you look at switch capacitor circuit, that's probably, I find this is the easiest way to analyze them, to do this. Anyway. You can look at the output. If you look at the output at clock phase 2, and sometimes you want to do, then you look at it half a clock period earlier, so you only get half a clock period delay. So you get set to the minus half in the numerator down there, if you look at that. Yeah, okay. There we go. Okay, very good. Any questions to this? Okay, so this is not how you normally do it. The reason that this is not how you normally do it is that this is sensitive to stray capacitance on this node here. So we've got capacitance on the drains of these switches. They will sit in parallel with that. They're voltage dependent, so that will create distortion. And also we'll not get exactly the transfer function we want. So what you normally do is you have a stray insensitive implementation. So what you do here is you put the capacitor that you have in series, like that. Like that. Okay. So C1 and C2. Let's have a look. So if we're doing clock phase 1 there and 1 there and 2 there and 2 there and look at clock phase 1, then it's almost the same as what we had before. Now it doesn't matter what the capacitance on these nodes here are. In one, that node in one phase is shorted to ground, in the other phase it's at virtual ground, so this node voltage doesn't change. That node here, the capacitance to ground here is just going to be charged to whatever that voltage source is. It doesn't change the charge flowing in here. So with this switch arrangement, you can see in clock phase 1 we have current flowing into the capacitor down to ground, so we're going to have the capacitor charged up, positive sign that way there. And in clock phase 2, we then, we've got virtual ground here and ground here, so we're going to charge it, discharge it, but now the current has to flow into the left. So we're going to charge up the capacitor. So it's going to be the same transfer function, except that the charge now in C2 now flows in the other direction. So that means that in this case we get the transfer function, which is now C1 and C2 times Z2 minus first divided by 1 minus Z2 minus first. So same as before, but we drop the minus. Now dropping that minus is actually important, because if we go back here and we look at the structure and seeing, what did we have up here? We're going into the negative input and out, so we need to have a minus on that. Now if we got rid of this minus here, the only thing we did was change the resistance. So what happens now is that resistance that we have is actually negative. If you have a voltage on the resistor, we get a current back to us. So that can be a bit tricky, because when you put this in a feedback loop, because you want to make a higher order filter, this is a negative resistor. So you've got to think about that. The other way that you can operate this is that you swap the clock phases. So you do phase 1 on these ones here, and then you do phase 2 on those. Now what that is going to do is that during clock phase 2, you're shorting both sides of this capacitor to ground, so you're discharging it. And during clock phase 1, you charge it up to the same polarity here, but that current now flows into that and through that capacitor. So now it flows in the same direction in C2 as it did before. But if we look at it at the output of clock phase 1, we don't get a delay through this. If we change during clock phase the red clock phase 1, if you change the voltage here, you will see the voltage change immediately at the output, which means that we don't get this set to the minus first now. So we have h of set equal minus C1 on C2 times 1 divided by 1 minus set to the minus first. Okay. If you look at it at clock phase 2, we get half a clock period delay. We can do that as well. It depends on where you feed it in. It depends on where you feed it in a system where you have clock phase 1 or clock phase 2 sitting at that point there. Yeah. Okay. So this is basically integrators. And once you can make an integrator, we can make anything, any filter. And yeah. So these are the most accurate filters you can make on chip, probably the switch cap filters. Yes. Okay. Any questions to this? Now you can also make amplifiers. So this is another common technique in switch cap. I'll just show you an amplifier, and then we have a break and do the paper. So switch capacitor amplifier. So let's have a look here. Now, what is neat about that, the switch capacitor amplifier, is that you can actually offset compensate it in one go. So let's see what I have C1 there and C2 there, and then we switch this one here to the in, and clock phase 1, clock phase 2, clock phase 2, clock phase 1, and clock phase 2. Okay, so in clock phase 2, what we have is the voltage across here. This is the offset voltage of the op amp. Okay, so in clock phase 2, we connected a negative feedback like that, so the output voltage is the same as the input voltage. So we have the offset voltage as a negative terminal. That is sample across that capacitor. It is also sample across that capacitor up there, which is nice. So we get here during clock phase 2. So in clock phase 1 then what we do is we have a change here. So the voltage on negative input is going to be the offset voltage at all times. Okay, so during clock phase 1, we're charging it up like that, and we got a change which is V in divided by C1. It doesn't matter what the offset voltage is. So we've got a charge flowing in there, delta Q, which is V in, so in that direction here, C1. So that flows up here as well during clock phase 1. And that means that the output voltage now is going to be, so the initial voltage on that side was ground. We have changed, we have that charge there flowing in C2. So the output voltage here is going to be, during clock phase 2, that's going to be equal to minus C1 on C2 times V in. So we want to look at that during clock phase 1. Yeah. So no offset on that. Yeah, but it's nice. What you can also do, but you don't have time to look at that, you can actually also, with these sort of structures, if you sample twice, you can also compensate for the finite gain of that. So you can essentially square the gain of the amplifier by sample the input voltage that you have for the expected output voltage, and then yeah, you can get You don't need to have a high gain in the amplifier if you do. It's call it a double sampling if you sample it twice, but no time for that.
Triple sample, will you get a Q?
Hmm?
You triple sample, would you get a Q? Like, are we essentially
I guess you could.
two filters?
I guess you could, but what you've got to do is to sample. You've got to have an estimate of what the output voltage is going to be. Then you sample the input voltage, and then you apply your input signal and see what the output voltage is. And if that doesn't change very much, then you're pretty good at what you have. But you could sample the input voltage twice. You sample the input voltages, then you get an output voltage. You sample what you have at the input of your op-amp, which is the offset plus the gain error that you have. You sample that on capacitor, and then you do it again. And you could keep going and really get, I don't know, infinite gain if you have an infinite time.
You sort of just driving that gain error.
Yeah, you can, yeah. Okay. All right, I think it's time to have a break. So let's break and then meet again. I say 25 to? Yeah. Let's do that, 25 to. That's like in 8 minutes or something. Okay. Yes.
Is there a rough list of the stuff?
A rough list of the stuff that we did cover.
Yeah. Was there any part of the first half of the lecture that we didn't cover? Like last week we didn't do bandcounts.
Oh, that we did not cover.
Yeah.
No. Yeah. Look, there's. Yeah. No, I don't have a list of what we didn't cover. I mean, it's not applicable to you, but it's not going to be in the exam if I didn't do it in the lecture. But yeah, look, there's we could spend the whole week talking about circuits every week, and they would all be relevant,
It turns out to me like it's like these haven't changed since like the 80s or 90s. Just a lot of these circuits. So it's almost like you think electronics is so complicated. Like we can compensate for this, we can add an extra circuit for that. And they do get a little bit complicated, but it's like the fundamental physics. Like you can just do the maths. It's like that linear cadence.
Yeah.
And then once you do that, there's no more to be.
So I think the way where it really changes is how much is ending up in the digital domain. So the amounts of the analog bits that you do, it doesn't change because the physics is the same. What really changes there is the parameters of the transistors, how good they are. But they're still working in the same way. So probably the main difference in what you have is the presence of gate current. This is throwing in a spanner on the wheels in some point. So if you look at having cascodes, traditionally you can just keep powering cascodes on until you get sick of it or run out of voltage. You can't do that if you have gate current because you're going to load it. And that's going to limit how high impedances you can get. It's also limiting the matching that you can get because the gate current is causing mismatch and stuff. So this is quite important. It's kind of a significant change. The other thing is that I guess the intrinsic gain of transistors that you have is much smaller in really short line with technologies. And that means there's stuff you can't do. Normally the way that people get around it is that they just use some old-fashioned transistors. They use high-voltage transistors. And if you're designing in a 20 nanometer process, you use the 1.8 volt transistors, then they look exactly like what they did in a 180 nanometer process, pretty much. So you would just back to use those transistors for the circuits where the analog function really matters to you. So you don't get a lot of gain in getting digital for that. So there the change. Yeah, they have less. Well, they have less transconductance, but they have high output impedance, so you can get higher RL gain in them. So the main difference comes in bits that becomes digital. Like that digital amplifier we looked at the other day. So the digital amplifiers, they're not, I think, used very much. but that was a cute idea. But what you are using is you're using digital LDOs, you're using digital PLLs, where there's still bits of it that's in an analog domain. In an LDO, for instance, the output voltage is analog. But what you do is that you wrap it around a digital comparator, and then you close the loop in the digital domain and switching, and maybe have an AD, sort of DA converter sitting in there, or you can do switching. But essentially, the control system becomes digital, and then you just have a couple of analog components around the digital control system. The same thing with digital PLL. That what you do. This is a new circuit, relatively new. Is a time to digital converter, where you look at what is an AD converter in time domain. So you look at two time differences and you make that into a digital number. So you use that in a PLL. You measure the phase difference essentially at the input, and then you digitize that directly, and then you have a digital control system that then drives a digital oscillator, so a digital control oscillator. So many of these, so this is quite common. This is happening kind of more and more, if you like, that you move stuff into that digital domain. But whatever wraps around it is still the same circuit settings you have got to do, but it just becomes thinner and thinner. If you like. Yeah.
It's a great lecture today. This is big stuff.
All right. Let me get the paper up for you. Just a sec.
Can we use our own laptop?
Yeah, sure. If you want to, you gotta be able to. Have you got a VGA or is it an HDMI input? There's an HDMI cable over here. What have you got? What ports have you got?
Like Type-C, USB-C.
Type-C. There is a Type-C here. I don't know if it works, but you can give it a go. No USB-C laptop. Oh, there you go. It worked. First time. Wow. This is. Yeah. Okay.
This one is about this second one. Like, I can't really imagine how that works. Yeah. So like. Yeah. So during phi 1, this charge, right?
Yeah. So during phi 1, you charge the input capacitor. Yeah.
But during phi 2, it's all disconnected.
No, it's kind of you connect phi 2 there and there, so
yeah,
that
the second one. Like the.
So during phi 1 you connect the capacitor up here. During phi 2 you connect the capacitor up like that.
Second one, not this.
Oh, during the second one. Okay, so during phi 2 you connect both of these to ground. During phi 1 you connect both of these. Yeah, so you got virtual ground here. So you connect this one here to virtual ground. So you've got 0 volts here, and then whatever voltage you change here is going to charge this capacitor up directly.
So it's charged during phi 1, right? Yes. Then so you disconnect this from the circuit technically during phi 2. So so I think it's first. This must be like charged. This must be charged up until full first before this one works.
So in clock phase 2, both of these is connected to ground, so it's discharged.
So it's charged.
Oh, no, yeah, gotcha. Yes, you start.
And then during clock phase 1, you connect one to virtual ground and the other to the input voltage, so you charge it up to the input voltage. Now the charge flows into that because it's connected to the virtual ground that you have to have current flowing in.
So it's connected until both these two are fully charged.
So you always wait until the charge is settled.
Oh, okay.
Yeah. Every clock period.
But for this one, actually, they are not another way for the both the capacitor's charge has been settled because it's actually in and we are the
No. You make the assumption that it always settles completely.
Like I was thinking that during the first one, like it works even when it's not settled, right?
There's no calculation in the result.
Yeah, but that's not normally how you use them, because the normal assumption is a switch capacitor circuit is that you wait until it's completely settled every time.
Oh, okay. No, that makes sense.
Yeah.
It's assumed that the clock frequency punch is high.
Yes. That's right.
But actually, this so the error can be made.
You got the translation.
Yeah. So you assume that the clock period is long enough so that the RC time constant in charging and discharging the capacitor, you can ignore that. It's charging up completely.
We have
Almost so many characters.
each node has a square wave.
Just a little square.
Yeah, or it settles.
Just settled just almost
Well, it doesn't need to be shut, it needs to be settled. And when it goes on, it's going to be flat.
because the charge is this charge rather than the voltage. Everything in the state.
Of course.
The charge and the voltage is two sides of the
If
same
you
thing.
want to
And then
talk
I- and
about
then
the
I
solution
ramble.
first,
Then I ramble about this for like.
Yes, but
I ramble about this stuff.
of course,
I'm probably gonna ask like about the on resistance.
I don't think we need to take too long.
Oh yeah, we don't.
Yeah.
Like I'll keep myself quick.
Yeah,
we don't-
this is why the
Yeah.
charge and the capacitor
I will
go
try
like
to
an exponential.
just
Like you can make your part quick, but you can ask questions. And it's fine if they take long with the questions. Like toss in my input or something. Like, doesn't matter. Like, I'll probably just like talk about the on resistance and talk about the
just a little
topology.
free about
Maybe we gotta talk about it later. Let's get everything.
Oh, this is the end.
I believe
They made it, didn't they? But they didn't.
They actually assume all the resistors are ideal switch, but all the simulation results is pretty.
They also only have one input voltage. They only tested for one input voltage. I mean, I think you can trust what they've said, but they haven't said.
Before that,
They have to test a little bit more.
Yeah.
so it's normally using biomedical.
Just
I like how they did the temperature test.
scenario where I have
Like they cycled that shit 100 times.
high frequency error.
just accelerate.
yeah, so you've gotta,
Accelerate. Aging.
you need to make sure that the signals
Yeah, that's what I thought it was.
are slow compared to the clock. That's a sample system.
Simulating a long life.
Start.
No. Well, that depends. The accuracy that you want. At 10 times. No, it's, how far down below the microscope can you go? It's a sample system. So you gotta, in principle, you have to sample twice as fast as your signal frequency. But that is flying really close to the sun.
I really worry about that resistors.
All right, shall we carry on?
Yeah. So shall we start?
Yeah,
Okay.
go ahead.
So, hey everyone, I will introduce a new topic, 2/3 and a half reconfigurable switched capacitor DC-DC converter, which shows a high energy efficiency in dynamic voltage. And first, with the popularity of the multi-core microprocessors, and we need to perform fine dynamic voltage scaling for each core, and integrate voltage regulators, which is RVS, provide an effective solutions. In this paper, an IVR with efficiency over 90%, and power density over 50 millivolts per millimeter squared is required. And this design is based on 180 nanometers CMOS process and 100 nanofarad multi-layer ceramic chip capacitors, which is LECs. Those are integrated on the chip, which improve the efficiency of the capacity management. And the key to this involvement is driver amplitude doubler, which is the DAD, and shows as figure 3 the circuit. Yeah. The half swing driver in the traditional design leads to a large resistance loss. So while the DAD technology that the paper proposed is reduce the loss by sampling the 1/3 of the input voltage from the flying capacitors, increasing the gate swing for the power MOSFET from the half swing to the full swing. Actually, there's a little question about the DADs. Since the DAD just increased the swing range from the half swing, which is 1.8 volts to the 2.7 volts, to the 0.9 volts to the 2.7 volts. The Bach circuit can do the same thing. So why we want to use DAD rather than Bach in this circuit?
So what can use the same thing?
Bach circuit. Bach. Just
Bach circuit.
Bach and boost. Just reduce
like a
the
non-switched cap, like a inductor capacitor Bach circuit. This is a Bach circuit.
Yeah.
It's in the power electronics.
Because if you want to use a Bach circuit, you have to use some extra components like inductors.
Inductors.
Sorry?
Bach is inductor.
Yeah.
Okay, so when we say Bach circuit, we're talking about like an analog capacitor inductor, normal Bach.
You may think of like power circuits, like buck converter.
Yeah, Bach converter. It's just a.
This one doesn't need big inductors?
Yeah, it's just the design target of this works is seeking for a high efficiency. If we just use the inductors, may actually cost more energy loss.
Really?
Yeah. Oh,
Well, it depends on where you want to put the inductor. If you want to put it on chip, then
No, yeah, I'm talking about like, because ideally an inductor is lossless, right? So I'm not sure why.
ideal inductor, of course, they don't have that kind of loss.
Yeah.
But
So like, I would say this theoretically would be less efficient than like a.
theoretically it is.
yeah,
If you scale down, will the inductor perform ideally?
Yeah.
yeah.
No. So we want to use capacitors.
So the reason we use this is we can fabricate this on a chip. It's not like some big bulky external thing, which is very inefficient.
I mean, you can have inductors on chip, it's just they're not nice.
So basically, this.
What you got to do with inductors and chips, because they're very small, is that you've got to switch it at really high frequency. If you switch it at at gigahertz or something like that, if you switch it at that frequency, you get a lot of switching losses, and that is just all not very power efficient. Sorry.
So for this work is actually trying to enlarge the gain source voltage to make the here's the as the figure 5. It's trying to enlarge the gain source voltage to make the transistor working in strong on conditions. So so that the converters can achieve about 90
93% of the efficiency and 62 million volts per millimeter square. And
Sure. So on the on resistance thing, if you look at the circuit here, or I can draw a graph for you. So when you have transistors in triode, which is what these transistors are in, if you increase the VGS, the gradient in the I VDS increases, which means a decrease on resistance. So we want less resistance to have less losses across the circuit. Now, looking at the circuit, you might be wondering how the hell that works. It's showing the two-thirds configuration, so making the voltage go down to 2/3. And the way it's doing that is that if you look at this one, you've got V in connected to V out through two parallel capacitors, because you've got a parallel path up there and a parallel path up here, or down here. And in the other one, you've got them in series. So they've changed from parallel to series. And I did some math. I don't think you don't have to trust it, but I got 2/3. It's kind of like, I don't really want to explain it, but like, it's kind of like the charge stuff that Torsten showed in the class, where like I've set V in and V out, and then I've like, this is for like over a long time, so this doesn't, I'm not sure if this analysis is correct if it's switching really fast. Because I made that assumption.
That's the idea. So
Yeah.
if you do that analysis, you assume that the charges settle on the capacitors.
Yeah.
And then if you switch it for a long enough time, this will settle in such that the output voltage is equal to 2/3 of the input voltage. It doesn't matter.
Yeah. So
the two capacitors, it doesn't even matter if the two capacitors are the same, because they have the same voltage. Or maybe they have to be the same in that.
I think they have to be the same to have the same.
Yeah, maybe they do there.
Because so it's like the voltage cross capacitor is V in minus V out in that configuration as time as it settles, and it's like V out over 2 reach capacitor, and then it works out as 2/3.
Yeah, well, that's the right analysis.
Yeah. So you might be wondering how it changes from 2/3 to a half, because you've got two different voltage configurations. What I think is the way it works is, if I can, no, I want to get the pen out, the red one. I'm pretty sure this one, great. This one turns off, and then these turn on, like that. So then it's parallel in that phase and parallel in that phase. And so it's basically the same as just having one capacitor. Like, if you just had, like, that. My lines are a bit bad. That, and then for this one it was, yeah, just one, yeah. And I'm pretty sure that would come out as half. So this is my handy wavy analysis of how the circuit works.
Yeah, no, that will work. Yeah.
And yeah, I've talked about the on resistance. So, do you want to talk about the results?
Yeah.
Sorry. I kind of forgot about the entire point of this paper. Like we said earlier, they wanted to increase VGS to decrease the on resistance and improve efficiency. And the way they improve VGS for specifically I think it's these weak ones, and maybe one of the other ones, is that they changed how the clock works. So instead of having the clock, and you go back up again, instead of having the clock go to V out at the bottom here, it goes to Vx, where Vx is lower. So that doubled the amplitude here, and that allows a bigger VGS on the transistors. How it works. The reason, so firstly, if we ignore the CX2 block, CX1 is just being charged to 0.9 volts when the circuit has that 0.9 volts, and when it's not, it disconnects. However, the problem with that is that there's also charge coming through here, which would make the voltage rise above 0.9. So they kind of have the CX2 block to keep it lower by turning it on when that Q1's being pushed in. Do you have anyone have any input to this, or like a better explanation? No.
No, you should charge. You can make CX1 infinite, and then it doesn't matter if you have a little bit of charge flowing into that. But what you can also do is you have charge being injected into that. You can remove that charge. So I guess the point is that the total capacitance sum of CX1 and CX2 is smaller if you.
And they show here how if they just use CX1 by itself, they have to make the capacitance really large to make it reach 0.9 volts. However, when they use that switching CX2, they could have an 84% reduction. I'm guessing what I'm saying there. So
that's a big capacitor, like a freaking nanophone.
And these are the off-chip ones, right?
yes, they're like MLCC, whatever.
Not that
means.
one, I don't think.
Oh, yeah, CX is internal, and then the fly ones and in and out. Yeah,
Yeah, so
They're
makes
off,
it important.
they're small.
You could make this one external, right?
You could.
Yeah. This means you don't have to.
Okay, we can actually go to results now.
All right. Let's go to the results. Yeah. We can see in the figure 9, right? It's a layout of the total design SC DC-DC converter. We can see it includes a 100 nanofarads overall to multi-layer ceramic chip capacitors. We can see in the it's blue in figure 9 on the left, which is capacitor in fly 1, fly 2, and out. And between it is 9 transistors from M1 to M9. And we also can see it on PCB. Its size is 0.2 millimeter times 0.2 times 0.4. Yeah, and given the coefficients of thermal expansion between the MLCC, like the multi-layer ceramic chip capacitors and silicon diff, it's crucial to verify the reliability of the mounting. So a thermal shock test is used to resolve it. We repeat this test for 100